So the brightness reaches about magnitude 2.5, and that's astronomer lingo for about the brightness of the North Star is about magnitude 2.5. Many people think the North Star is bright and distinct in the night sky, but it's not. It's just not. Like, get over it. The North Star is not in the top 10. It's not even in the top 40. The North Star is the 49th brightest star in the night sky.
So, why does a fairly ordinary-looking dot in the sky get treated like the king of the night? If you walk out under a dark sky, the star we call the North Star does not jump out as especially dazzling. Yet, physically, it is a monster. It emits thousands of times more energy per second than our sun. The trick is that what your eye judges as bright is not a direct readout of a star's power. Astronomers separate two ideas: apparent brightness, which is how bright something looks from Earth, and luminosity, which is the total energy it emits in all directions. A car's headlights look dim when it is far down the highway, but you know the bulbs did not get weaker, and the light just spreads out. Stars play the same game, and that is the first clue to why this one star is so culturally important, despite its modest appearance. The striking thing is this: its fame comes from geometry, not from brilliance. Earth spins around an axis, an imaginary line running from the geographic South Pole to the geographic North Pole. If you extend that line far into space, it pierces the celestial sphere, the mental dome on which we imagine the stars to sit. The point where the axis meets that dome in the north is called the North Celestial Pole. The North Star happens by coincidence to lie very close to that point. Because of that alignment, as Earth rotates, most stars trace long circles across the sky, but this one hardly moves at all. For someone in the northern hemisphere, it marks true north to within about a degree. Sailors and travelers used its height above the horizon to estimate their latitude. So, even though its light is not exceptional to your eyes, its fixed position made it exceptionally useful, which starts to answer why we care about it so much. But why does the sky mislead us so badly about which stars are truly powerful? The main reason is the way light spreads. As light travels outward from a star, it spreads over larger and larger spheres. If you stand twice as far away, the same total light is now smeared over 4 times the area. So any one patch, like your eye, receives only a quarter as much. This is known as the inverse square behavior of light, and it follows directly from simple geometry of spheres. Imagine 3 identical street lamps placed 1, 2, and 3 city blocks away. The farthest one is still just as bright in itself, yet it appears 9 times dimmer than the closest. When we look at the night sky, we are seeing stars at vastly different distances mixed together. Some of the faint little specks are genuine supergiants, burning tens of thousands of times more intensely than the sun, but so far away that our eyes barely register them. Some of the boldest stars are just nearby, fairly ordinary stars. Our impression that the North Star is nothing special is mostly a distance illusion. On top of that, this modest-looking object doubles as a precision measuring instrument for the universe. It belongs to a class of stars called variable stars whose brightness changes over time. A specific type, called a Cepheid variable, brightens and dims in a regular rhythm, like a very slow, steady heartbeat. Observations in the early 20th century revealed something crucial. For Cepheids, the period of that cycle, the time from bright to dim and back again, is tightly linked to their true luminosity. Longer period means higher luminosity. Nearby Cepheids have had their distances measured directly by parallax, the tiny apparent shift in position as Earth orbits the Sun. That lets astronomers calibrate this period luminosity link. Once calibrated, a Cepheid becomes a standard candle. By timing its pulse and measuring how bright it appears, we can infer how far away it must be. This method has been used to measure the distances to other galaxies. So by watching the subtle flicker of a single star, we can estimate the scale of structures millions of trillions of kilometers away. The North Star is a somewhat quirky key feat itself, and that makes it not just a directional marker, but also a laboratory for these distance techniques. What does it mean that our most trusted point in the sky is both contingent and temporary? Earth's rotation axis is not perfectly fixed in space. Because the Sun and Moon pull slightly on Earth's equatorial bulge, the axis slowly traces out a circle, much like the wobble of a spinning top as it slows. This motion is called precession. It takes roughly 26,000 years for the axis to complete one full loop. As that happens, the north celestial pole drifts among the stars. A few thousand years ago, during the time of ancient Egyptian civilization, a different, relatively faint star in the constellation Draco lay near the pole. About 12,000 years from now, the bright star Vega will be the go-to northern marker. There will also be eras when no bright star sits conveniently close to the pole at all. So the idea of a single eternal north star is an illusion created by our short human timescale. Its central role in navigation is a feature of our particular historical moment, not a permanent property of the sky. In the end, the North Star is important not because the universe granted it special status, but because it exposes how much of astronomy is about correcting for our own perspective. It looks modest, yet it is an enormous, evolved supergiant, pouring out energy thousands of times faster than our sun. It anchors our sense of direction only because Earth's axis happens to line up near it right now, and that slow cosmic wobble means its reign is temporary. Its rhythmic variations participate in the cosmic distance ladder, helping us connect the scale of our local neighborhood to the scale of distant galaxies. So, why does this unassuming point rule our maps and stories? Because when you combine the physics of light and the geometry of rotation and the careful analysis of tiny brightness changes, it becomes a natural reference point in both space and distance. An alien civilization on a planet orbiting another star might or might not have a bright star conveniently close to its planet's rotational pole, but if it did, that object would play the same geometric role as our North Star. They would build a different sky lore around whatever markers their sky provided, yet by applying the same physical principles, they could still infer the same large-scale structure and laws of the universe. That is the deeper lesson. Astronomy takes these very local, accidental alignments in our sky and, by stripping away illusions of brightness and direction, turns them into reliable guides to the cosmos itself. Like if this was interesting, and hit the subscribe for more.